In this video, we're going to look in detail at a particular type of reaction called acids and base reactions. We're not going to look as much at the reactions here, but just talk about general acid and base theory and what makes something an acid and what makes something a base. Acids in general are another thing we find that realistically are talked about in sort of everyday language and in pop culture much differently than what they really are. You hear the term acid, and most people immediately think, oh my God, melt my face off. Something that's very dangerous, and it's, you want to be very, very careful around it. And certainly that's true of some. There are definitely some melt your face off acids out there. I once did an experiment during undergrad where we needed to find the amount of calcium in a can of sardines. And to do so, we had to literally dissolve all of the sardine bones. And we used boiling sulfuric acid to do this. Very, very dangerous thing. But the reality is that the term acid and the term base really just refer to one way in which compounds are going to behave chemically. Now, in some cases, yes, that can lead to a dangerous situation. But as we're going to see with what we talk about here, water can be considered to be both an acid or a base. Water's not that dangerous. And so keep that in mind, that really the terms acids and bases, they refer to how something is going to behave chemically. They give us a way to be able to predict certain things about their behavior. There's a couple of different ways that we define acids and bases. One of them is by using what we call the Arrhenius definition. In the Arrhenius definition of an acid is any substance that will produce more hydrogen cations when placed into water. And so think about this example. Think about if we have some HCl. If we have some HCl and we put this into water, that is going to split up into its ions. We're going to have H plus and Cl minus. And so we have increased our amount of H plus ions, which means that HCl is an acid. Or HNO3 will split up into H plus and NO3 minus. Again, polyatomic ions, NO3 is nitrate. Just one of the reasons why it's important to know those. But so that makes this HNO3 an acid. And in fact, this is called nitric acid. The first one here, this is our good old friend, classic hydrochloric acid. And so that's the general behavior of an Arrhenius acid. Anything that when it's dissolved in water increases the amount of H plus in our solution. It's also important to note that when hydrogen ions go into water, they actually end up bonding with a water molecule to form this hydronium ion, this H3O plus. And so we have this H plus here, gets added to water to form this hydronium ion. You'll quite often, just for ease of writing, you'll quite often see those used interchangeably. Sometimes, like in the top examples, I just wrote H plus, and you'll see that quite a bit with people writing out these sort of dissociation equations of acids. But it is important to note, again, that H plus really means we have H3O plus in the actual solution. So just keep that in mind, that that's the reality of what we have, is that hydronium ion. An Arrhenius base is anything that increases the amount of hydroxide ions, anything that increases our amount of OH minus. Hydroxide containing salts, therefore, are always bases. And so something like sodium hydroxide, NaOH. If we take some solid NaOH, dissolve that in water, it's going to do what ions do in water and split up into Na plus and OH minus. So we have increased our amount of hydroxide ions, making sodium hydroxide a base. Calcium hydroxide, CaOH2. So it is split into its Ca2 plus and 2 OH minus ions. So calcium hydroxide is a base. And so we can use the abbreviation of M to just stand for any metal. And so any metal hydroxide will always behave the same way. We'll split up into its metal with whatever its charge might be, but then plus the OH minus, our hydroxide, meaning that all metal hydroxides are going to be bases. Now the Arrhenius definition though, sorry, I skipped a slide there, touchy again. We're going to look at these neutralization reactions in a later lecture, but we should also note that when the proton, and actually let me back up so we can see another term for just a second. Let's take a look at this. If we have an H plus ion, if we remember if that hydrogen, let's say we just have a standard hydrogen 1 atom, that hydrogen 1 atom has 1 proton, has 0 neutrons in there. Sorry, my whiteboard's going nuts. There we go, 0 neutrons, because remember mass number is our protons plus neutrons. Hydrogen 1 only has a mass number of 1. We know it has 1 proton, that's what makes it hydrogen. So it must have 0 neutrons in there. And it's going to have 1 electron. The hydrogen plus ion still has its 1 proton in there, still has 0 neutrons, but now it's also lost that electron. So that means that H plus really is just 1 lonely naked little proton hanging out. And so you'll see that used interchangeably as well. You'll hear somebody say proton when talking about acid-base chemistry. When you hear the term proton like that, know that this is really what we're talking about, is just an H plus. So I wanted to point that out because you are going to see that, and you see it here that I just sort of dipped that in. Oops, sorry, go back. So the proton from an acid, meaning the H plus. So whenever a proton from an acid is combined with a hydroxide from a base, a water molecule is formed. That's how acids and bases end up being neutralized, is the H plus from the acid reacts with the OH minus from the base and just forms water. Again, we'll look a little bit deeper at those reactions in a later lecture. Oh, and I'm not sure how that happened, but there's a whole bunch of my photos. You can see there, oh, yeah, you can see they're mostly pictures of Henry. And one of a grill full of meat. Oh, there we go. That was showcasing his bug bite. Look at that. That's nasty, isn't it? All right. Anyway, sorry. Enough of him. So that's the Arrhenius definition of acids and bases. We also have what we call the Bronsted-Lowry definitions, because it turns out that there were some substances, especially when it comes to bases, there were some substances that were exhibiting base behavior, but that didn't necessarily increase our OH minus. And so we needed to have a different way to look at things. Turns out in this case that this one, ammonia, does, but there were others that didn't. And so in the Bronsted-Lowry definition of acids and bases, we look at an acid as being a proton donor. And so anything that's going to donate a proton, donate an H plus to another molecule. A base is then a proton acceptor, anything that's going to accept the H plus from that other molecule. And so this makes it possible for us to also see how molecular compounds behave as bases. And so ammonia, we can see here NH3 is a base because it's going to accept an H plus from water. So as we go from one side to the other, we can see that ammonia goes from NH3 to now being NH4 plus. And so one of these hydrogens from water left water, sorry about that, left water and joined onto the ammonia. Similarly, water here, so we can see that water is acting as an acid because it's donating. As we go from one side of the equation to the other, we can see that the water is losing its H plus to form this OH minus. And so water is acting as an acid because it's donating an H plus. And so that's just another, it's another way for us to look at acid and bases behavior is by this donating and accepting of our proton. And so when we look at what does happen when an acid dissolves in water, again, we have here's our HCl plus water. And so now this hydrogen from the HCl is going to come onto the water molecule to form that hydronium ion that we talked about. There's our H3O plus. And so the HCl is donating a proton. It's donating an H plus. That makes it an acid. The water here now is acting as a base because it's accepting an H plus. And that's going to result in what we call a conjugate acid-base pair. And so we can see here that Cl minus is what we call the conjugate base of the HCl. Because if we look at the reaction in the opposite direction, let's look at the reaction going from here up to here. Cl, in this case now, is accepting a hydrogen, which makes it a base, the Cl minus. The chloride ion accepts a proton, making it a base according to the Bronsted-Lowry definition. Our H3O plus is donating the proton as we move this direction. So this H3O plus is behaving as an acid. And so that means that this HCl and this Cl minus, these are a conjugate acid-base pair. This H2O and H3O plus are another conjugate acid-base pair. And we'll look at some other examples of that. And so conjugate acid-base pairs, after transferring a proton, what the acid then becomes is known as the conjugate base. After it accepts a proton, the base is now known as a conjugate acid. The acid and its conjugate base and the base and its conjugate acid are known as conjugate acid-base pairs. And you can really see that in action here. So here's acetic acid and water. And so we can see that acetic acid, as it moves from one side of the equation to the other, is losing a proton. And so here it's the acid, it's going to lose the proton. So we can see that proton is lost now over here, whereas the water is gaining that proton. Water is going from H2O to H3O plus. And so that makes acetic acid and our acetate ion over here a conjugate base pair. The acetic acid lost the proton to become the acetate ion. And so the acetate ion is the conjugate base of acetic acid. Just as the hydronium ion, our H3O plus, is the conjugate acid of the base, which was water. We see it here with nitrous acid. So our HNO2 is going to NO2 minus, so it's donating a proton. And so we go from an acid to our conjugate base. The H2O is gaining a proton, and so it's going from a base to a conjugate acid. There are some molecules that could either act as an acid or a base. Those are known as amphoteric molecules. And so we've seen this in a couple instances already. But we can see that in this example here, if we have HCO3 minus, we can see that water is going to act as an acid in this example. Because in this example, HCO3 minus becomes H2CO3. So this is our HCO3 minus is accepting a proton from water. And so that must be our base, which means that water has to be our acid in this situation. But in this one, now we have HCO3 minus, so same thing, but instead it's going to form the conjugate base. It's going to lose its additional proton to form CO3 2 minus. And so this means that HCO3 minus could go in either direction. HCO3 minus could either gain another proton to become H2CO3, in which case it's acting as a base, or HCO3 minus could lose that additional proton, in which case it's acting as an acid. And so it could go in either direction. It's also important to note what hydrogen, what H plus can actually be donated from a molecule. In some cases, it's pretty obvious, such as in HCl, there's only one hydrogen here. That's going to be donated, and we're going to be left with the chloride ion. In something like acetic acid, very often you'll know which hydrogen can be donated because it's written in front. And so in acetic acid, you'll quite often see it written as HC2H3O2, and then that H is lost to become the acetate ion. And so that's another way to, and this isn't foolproof. You're not going to see this all the time, but a good part of the time, that is a good way to identify as well if something is an acid or not. If there's an H in the front of it, most likely that's an acid. The rest of that compound then is going to be what forms as the conjugate base. In order to predict the formula of a conjugate base, it's pretty simple. We start with the formula and charge of our acid. So in this case, HCl is our acid. We decrease the number of hydrogens by 1, remove a hydrogen. So we're going to go from HCl to just Cl. We also decrease the charge by 1, because remember, we're losing an H plus. That means we're going to increase the negative charge by 1. And so our conjugate base of HCl is going to be Cl minus. If we have H2PO4 minus, our conjugate base, we're going to lose one of the H's to become HPO4 2 minus, or sorry, to become HPO4, and we're also going to decrease the charge down to 2 minus. We could even go a step further with that one. If we have HPO4, this could be the acid still, so that can still be an acid, because we can lose another hydrogen still, decrease our charge by 1 to form our conjugate base of the phosphate ion. We can use a similar method to predict the formula of a conjugate acid. We can start with the formula in charge of the base, add a hydrogen, and add a 1 plus charge. And so let's look at an example of doing that with 2 different directions. So we looked at our HCO3 minus a little bit ago. That could go in either direction. So it could act as either an acid or a base. If it's acting as a base, then we would predict the formula of our conjugate acid by adding in an additional hydrogen. So you can see that happening here. We go from HCO3 minus to H2CO3. And we're going to add +1 to the charge, which gets rid of our -1 charge. So the conjugate acid of HCO3 minus is H2CO3. This could also act as an acid, though, and to find the conjugate base, we remove a hydrogen to get to CO3, and we increase our negative charge by 1 to go from 1 minus to 2 minus. Nope, I didn't need to talk about these tables. I shouldn't have left those in. Okay. The strength of acids and bases. So this is another thing to be aware of. When we talk about how strong an acid and base is, it doesn't necessarily mean how dangerous it is. The danger, so to speak, of an acid would be determined much more by its concentration. When we talk about strength of acids and bases, we're talking about how much they dissociate in water. Strong acids and strong bases dissociate completely. What that means is, for example, HCl, and we'll see our list of strong acids in just a minute, but HCl is a strong acid. And so if I start off with 100 HCl molecules, just as an example, when those dissociate in water, every one of those, every single of those 100 molecules is going to split up. And I'm going to be left with 100 H pluses and 100 Cl minuses. And at that point, I will have 0 left as HCl. That all split up into H plus and Cl minus. As opposed to a weak acid, something like acetic acid, If I start off with 100 molecules of acetic acid, and this is just a made up number, we're not going to worry about what the real numbers would be for this course. But not all of those are actually going to dissociate. In fact, very few of them will in this case. We might be left with 95 of the acetic acid molecules, and only 5 H pluses and acetate ions. So very little of it actually split up. Most of it stayed together in the molecular form. That's a weak acid. Now, again, that doesn't necessarily mean strength, or sorry, that doesn't necessarily mean the danger of it. HCl, if you're down to like, 0.001 molar, I mean, I'm gonna, not intentionally, because it's still a stupid lab practice, but I would pour that on my arm, not even really notice it. That's not really gonna hurt me that much. I take 10 molar HCl and pour that on my arm, now I've got a problem. Similarly with acetic acid, a dilute mixture of acetic acid, not going to hurt at all. In fact, I want to put that on my cucumbers. That's just vinegar. If I take glacial acetic acid, if I remember it at 18 molar, I dump that on my arm. Now I've got an issue. So again, I point that out just so that you recognize that when we're talking acid and base strength, we're talking about this behavior of dissociation. It's not necessarily indicative of how dangerous the substance might be. Bases are the same way. So a strong base, NaOH, 100% of that will split up into Na plus and OH minus. If we have a weak base, something like magnesium hydroxide, some of that splits up. Some of it just still stays together. So that's our definition of weak acids and weak bases. As far as bases go, our strong bases are any of our hydroxides that are made of group 1 metals. And so lithium hydroxide, sodium hydroxide, potassium hydroxide, even rubidium and cesium hydroxide, even though we don't talk about those two that much. But any hydroxides that are made with these group 1 metals are strong bases. Any bases made with the larger of the group 2s, strontium and barium, are also strong. As far as strong acids, so we talked about this a little bit. So again, strong acids completely dissociate. HCl is the only strong acid that's produced in our bodies. The HCl is stomach acid. It's like I mentioned, strong acids, very corrosive when concentrated, even weak acids, corrosive when concentrated, but pretty safe to handle when they're dilute. As far as our strong acids, I would memorize this list. This is our list of strong acids. Every other acid is considered a weak acid, but this is our list of strong acids: nitric, sulfuric, perchloric, hydrochloric, hydrobromic, and hydroiodic. All strong acids. Mentioned this already, but our strong bases can also completely dissociate, producing our hydroxide ions and our appropriate metal cation. They're strong electrolytes if they are soluble. Strong bases are also highly corrosive when concentrated, but fairly safe when they're dilute substances. And if you'd like, you could also simply just memorize this list, or like I said, memorize your group 1s and your larger group 2s. Oh yeah, calcium, barium, and strontium. Beryllium and magnesium, however, hydroxides are weak bases. And so, like I had mentioned, weak acids and weak bases don't dissociate in water that much. They produce very few ions in aqueous solutions, so they're also very weak electrolytes. Acetic acid is a good example. Acetic acid is one of our weak acids, so therefore it also makes a weak electrolyte. So it would only light up a light bulb just a little bit if we use that in our conductivity tester. And so there is our introduction to acids and bases. And so with that, good day, good evening, and good night.